When electricity is transmitted over long distances, some of the energy is lost due to resistance in the transmission lines. Let's use the voltage formula to explain why high voltage transmission is more efficient. V equals I multiplied by R, where V equals voltage in volts, I equals current in amperes, R equals resistance in ohms. When transmitting electricity over long distances, the resistance R of the transmission lines is constant. To reduce energy loss I squared multiplied by R, we can either reduce the current I or increase the voltage V. Let's say we want to transmit 1000 MW of power over a transmission line with a resistance of 10 ohms. If we use a lower voltage, say 100 kV, the current would be I equals P V equals 1000 megawatt, 100 kilovolts equals 10,000 amperes. Using the formula V equals I multiplied by R, the voltage drop energy loss would be V equals 10,000 ampere multiplied by 10 ohms equals 100 kilovolts. This means that 100 kilovolts of energy is lost as heat in the transmission line. Now, let's increase the voltage to 500 kilovolts. I equals P V equals 1000 MW, 500 kilovolts equals 2000 amperes. V equals 2000 amperes multiplied by 10 ohms equals 20 kilovolts. By increasing the voltage, we've reduced the current and subsequently the energy loss 20 kilovolts versus 100 kilovolts. This is why high voltage transmission is more efficient for transmitting electricity over long distances. High voltage transmission reduces the current flowing through the lines, which in turn reduces the energy lost as heat. High voltage transmission allows for more efficient transmission of electricity over long distances. This is because the higher voltage enables the use of smaller conductors, which reduces the weight and cost of the transmission lines. High voltage transmission lines have lower line losses compared to lower voltage lines. This means that more of the generated electricity reaches the consumer. High voltage transmission is more economical for transmitting large amounts of electricity over long distances. It reduces the number of transmission lines required, which saves on materials and construction costs. High voltage transmission systems are more reliable and less prone to faults, as they operate at higher voltages and lower currents. The most common high voltage transmission voltages are 115 kV, 230 kV, 500 kV, and 765 kV. These high voltages are stepped down to lower voltages like 120–240ths of a volt at substations before reaching consumers, ensuring safe and efficient delivery of electricity. HVDC high voltage direct current stations are facilities that convert alternating current AC to direct current DC, or vice versa, for the transmission of electrical power over long distances. They play a crucial role in modern power systems, enabling the efficient and reliable transmission of electricity across vast distances with minimal losses. Here's how they work. 1. Rectifier station. The AC power from the transmission grid is converted to DC power using a rectifier. 2. DC transmission. The DC power is transmitted over long distances through a DC transmission line, often underwater or underground cables. 3. Inverter station. The DC power is converted back to AC power using an inverter, which is then fed into the receiving grid. HVDC stations are used for 1. Long-distance transmission, reducing power losses during transmission over long distances. 2. Interconnecting grids, connecting asynchronous grids or grids with different frequencies. 3. Renewable energy integration, enabling the transmission of power from remote renewable energy sources, like offshore wind farms. The mechanical plant design team is responsible for designing the mechanical aspects of HVDC stations, including 1. Station layout design. 2. Building requirements inputs to civil designers. 3. Installation drawings and detail design of steel supports, connectors, insulators, etc. These designs ensure the safe, efficient, and reliable operation of the HVDC station.